Welcome, differential equation scholars, to the second video in our sequence on applications of second order differential equations. We've been looking at the motion of objects in a spring mass system and deriving equations of motion. In our first video, we took a look at what we called free undamped motion. What happens if we have a mass at the bottom of a spring and we move it to a certain position above or below its equilibrium point and we let it go, possibly with some initial velocity? How will it move? Well, we found out that taking into account the spring constant k, that the equation of motion would be of the form x double prime plus omega squared x equals 0, where omega squared is a constant that is the ratio of the spring constant to the mass of the object that's attached to the spring. And that second order linear differential equation with constant coefficients has roots that are equal to plus or minus omega I. They're complex roots, purely imaginary. And because of that, our solutions are going to be sines and cosines. The equation of motion will be C1 times the cosine of omega t plus C2 times the sine of omega t. We'll have oscillatory motion. Now that's an idealized situation. It takes into account only gravity and also the restorative force of the spring. But actually in practice, there are other forces at work. We know from real life that there are things like friction and air resistance, and those are going to tend to dampen the motion of the object that's at the end of the spring. It's not going to forever oscillate in real life between its maximum amplitude up and down. It's going to tend to dampen out and return to its equilibrium position. So we can create a more realistic situation by introducing what we call a dampening factor. And that's going to be a constant that we're going to call beta that we introduce into the equation. And beta is going to be a number that we're going to take to be, we're going to take the dampening force to be beta times x prime. You'll see it in the differential equation here. And that's to model the fact that in general, we probably expect the dampening to be responding to, or you might say proportional to, the current velocity of the object. The faster that it's going, we might tend to have more air resistance or more friction. And it'll be acting just like the spring constant in a direction that's opposite the force of the gravity. So we'll get an equation of m times the second derivative of x. That's our gravitational factor in the equation, plus beta times x prime. That's our dampening term, plus k times x. That's the term that's coming from the restorative force of the spring, all equal to 0. That'll be our new differential equation, taking into account the dampening. Now, if we divide by m, we can write that as x double prime plus beta over mx prime plus k over mx equal to 0. And that's a second order linear differential equation with constant coefficients. Now, the constants that occur there, the constants that are in front of the x prime and the x term, which will then go into our auxiliary equation, we're going to give them special names. We've already called k over m omega squared previously, but now we're going to introduce another constant, lambda. And we're going to say that this coefficient of our x prime term, the dampening constant beta divided by the mass m, we're going to call this twice lambda. 2 lambda equals beta over m, so that we rewrite our equation in this form: x double prime plus 2 lambda x prime plus omega squared x equals 0. Now, why introduce this lambda, and why 2 lambda in the middle? Why not just lambda? The reason for that has to do with what happens when we take look at the roots of the auxiliary equation. When we take a look at the roots of the auxiliary equation, which is the quadratic equation, m squared plus 2 lambda m plus omega squared equal to 0, according to the quadratic formula, the roots would be negative 2 lambda plus or minus the square root of 4 lambda squared minus 4 times 1 times omega squared divided by 2. And we notice that both of the terms now underneath the radical sign have a factor of 4 in them. So if I factor that out, square root of 4 is 2. So in the numerator, I'd have negative 2 lambda plus or minus 2 times the square root of lambda squared minus omega squared divided by 2. And you see, with that choice of convention for the coefficient, by calling that middle coefficient of our auxiliary equation 2 lambda, we now have the situation that that expression for the root reduces in a rather nice way. And it reduces to become negative lambda plus or minus the square root of lambda squared minus omega squared. That's a rather, you might say, a slick expression for the roots of the auxiliary equation, given those choices for lambda and omega. Now observe, of course, that because we have a square root, it's possible that our roots could either be real or they could be complex. If lambda squared minus omega squared is negative, then we're going to have complex roots. So we have to look at several different cases for what could happen depending on how lambda squared, which is a term that comes from the dampening, and how omega squared, which is the term that comes from the spring constant, how those compare and how they relate to one another. So let's take a look at 3 possible cases here. One case could be that the damping force, which is our lambda, which is coming from the beta constant, could be small relative to the spring force. If lambda squared is smaller than omega squared, which is what will happen if the size of beta is small compared to the size of k, then that radicand expression, lambda squared minus omega squared, that we had in the root will be negative if lambda squared is less than omega squared. And that's going to happen exactly when this dampening force is small compared to the spring force. Well, that means we're going to have a negative radicand means we'll have complex roots. And we know from our theory in chapter 4 what that means for the form of our solution. It means that our solution won't just be exponentials. The solutions will be exponentials times sines and cosines. What do we have? Well, let's go back and look again. Remember that our roots were of the form negative lambda. That would be the real part here in this scenario. And then we're going to have cosines and sines of this expression here times t. But because we're factoring out a negative sign from there to get the I, to get the imaginary part, the lambda squared minus omega squared will switch around and become omega squared minus lambda squared when we factored out the -1 to get our imaginary unit. So that means that the form for our solution here will be negative e to the negative lambda t. That's coming from the real part of the root. And that first part we're going to refer to as the damping factor, that negative exponential. And then it's going to multiply a sum of sines and cosines. We're going to have C1 times the cosine of the square root of omega squared minus lambda squared t plus C2 times the sine of the square root of omega squared minus lambda squared t. Now, this situation where the damping force is small relative to the spring force, that's what we refer to as underdamped motion. Because the damping force is not too strong, that means that we're still going to get oscillation for the system. but it's going to be oscillation that eventually is going to peter out. And eventually, because of that damping factor, that e to the negative lambda t at the beginning, that damping factor is going to drive the position of the mass towards zero as t goes to infinity, because we know that the function e to the negative at, that has a limit of zero as t goes to infinity for positive values of a or lambda here. So this is a situation where we will have oscillation, but it will be oscillating less and less until eventually the system moves toward that equilibrium position of zero. That's underdamped motion, when lambda squared is smaller than omega squared. But it doesn't have to be that way. It could be the other way around. It could be that the dampening force is larger relative to the spring force. If the dampening force is larger compared to the spring force, so that lambda squared is bigger than omega squared, and that lambda squared minus omega squared is positive, then we don't have complex roots at all. We have two distinct real roots. One of them is negative lambda plus the square root of lambda squared minus omega squared. And the other one is negative lambda minus the square root of lambda squared minus omega squared. So we have a sum of exponentials, if you will. The sines and cosines are gone here. And what that means in this case, where the dampening force is larger relative to the spring force, the dampening force is so large that we're not going to have oscillation at all. We're going to have a smooth motion of the position of the object towards its equilibrium point. We won't see the going back and forth above and below the equilibrium position that we had before. We're going to move just smoothly toward the equilibrium position. There will not be oscillation in the manner that we had in the first case where we had the complex roots. This is called overdamped motion. And it stands to reason that that would happen if you had such strong damping. If the dampening is stronger compared to the spring force, then you're not going to get oscillation. You're just going to get motion of the object back towards its equilibrium position. That's another possibility. If you have strong dampening forces, you might have an overdamped situation and no oscillation at all. There is, of course, a third possibility, the sweet spot, you could say, the place where the lambda squared and the omega squared are exactly equal to one another. If they're exactly equal to one another, then the situation is that we have only one repeated real root, and that is negative lambda. And so that means our solution will be of the form C1 times e to the negative lambda t plus C2 times t times e to the lambda t, because of the repeated root situation in our theory from chapter 4. This scenario is what's called critically damped. Critically damped is when lambda squared and omega squared are exactly the same as one another. In this sort of situation too, you can see we don't have any sines and cosines in our expression. So there's not going to be any oscillation here either. We're going to get smooth motion of the object towards its equilibrium position again, because of the dampening factor at the beginning, the e to the negative lambda t. But this is the place right here where, if there had been just a little less dampening than there is, and this is the reason why we call it critically damped, if there was even slightly less dampening in the situation than you're seeing, then the system would move into oscillatory behavior, because at that point the spring constant's contribution would start to, you might say, overwhelm or overtake the effects of the dampening. So we call it critically damped because it's kind of that sweet spot, that point of transition. If you'd have even slightly less influence coming from the dampening factor, you would move into oscillatory behavior from that critically damped situation. So there you have it. Those are three possible scenarios that we can have with what we call damped motion, where we're taking into account forces like air resistance or friction that tend to impede the motion of the object in a way that we take to be proportional to the velocity of the object at the time. In our next video, we'll take a look at a specific example of a mass spring system in motion, and we'll take a look at it in both an undamped situation, and then we'll add some damping and see what happens to it. But I hope this video has been instructive. This video goes along with pages 202 through 203 of your text. Hope this has been instructive, and we'll see you again at a YouTube channel near you.